So the next topic we're going to talk about router. What is inside a router? So we'll talk about the input port and the output port and how they do packet switching. And there are some buffering and scheduling problems. So the first one is like this, okay? So right here, let's take a look at the router, okay? A router looks like very slim and like a box right here, okay? They're usually in a data center, okay? They have many different ports, and usually a router should have 24 ports, 36 ports, for even 48 ports like this. Okay, they stack with each other. Okay. So when you have a router, okay, they should have several different ports. For example, we have 4 ports right here. Okay, so for each port, it has several different components. In this textbook, okay, we have the green one, blue one, and red one. We'll talk about what is it later. Okay, and usually you connect a line at this port, right? So currently the line space should be for router, okay, should be 1 gigabit per second to 10 gigabit per second. So that is the line speed. Okay, that is the line speed. So when this input port receive packet from the line, okay, it should pass the green component, the blue component, and the red component. So after that, okay, we have to decide where the packet should go, to port 3 or to port 4. So there should be a processing right here. So we have a routing processor. So basically it is simply just CPU, right? It should check it should check the packet. It should determine where the packet should go, okay, and do switching, which means switch the packet from one port to the other port. And as we mentioned, since we have 20, 30, or even 40 ports, and the input speed is quite high, for example 1 gigabit per second, so the intermediate switching fabric should run in a very high speed, so that the incoming packet will not queued in this router. Okay, so let's take a look at the right hand side. So at the right hand side, routing managing control plane, usually it is a software. So we need a software, we need a CPU to compute the routing algorithm, to check some important field, to manage the control plane. And those software usually it operates in millisecond time frame. Okay, and take a look at the forwarding data plane. Usually a hardware, okay, it operates in nanosecond time frame because it's a high-speed IC. Okay, so you have to think about one thing. When you have 24 lines, 24 ports, and all of these lines are backlogged, which means every second, we have input packet. And when we do such kind of high-speed switching fabric, at least your switching speed should larger than 24 gigabit per second if you have 24 ports and each port is 1 gigabit per second, so that your switching fabric will not be the bottleneck of this router. Okay, that is the idea. Okay, let's take a look at the input ports. Okay, as mentioned, we have 3 different component. Okay, so packet are received at the left hand side. So the first component is line termination. It is layer 1 component. Okay, layer 1, layer 2, layer 3. Layer 1 component. So no matter you use a fiber or you use a copper wire, okay, you have signal received from the line, and the line termination will convert the signal, no matter it is a digital or analog. It depends on what kind of line you use. Okay, you convert your signal to bit. So I write a bit right here. Okay, so usually it is a physical layer functionality, bit level reception. So after you collect a lot of bits, okay, it forms a frame, which is layer 2. So it is data link layer or link layer. We'll talk about Ethernet and Wi-Fi in chapter 6 and the following chapters. Okay, so after you receive a frame, and usually a frame is 150 byte. Okay, so it's around 10,000 bits. Okay, in a frame. Okay, we'll talk about frame later. Okay, so after you have a frame and you receive the diagram, right? You unpack the frame and you receive a diagram, right? So the diagram will be queued in a queue at the red component. Okay, those diagrams are wait to be checked and wait to be processed and wait to be forwarded to the output port. Okay, the reason why we have a queue here is because sometimes the switching fabric is a little bit slow, or is trying to find appropriate output port. So some diagram need to wait in this queue. Okay, and this queue is exactly what we mentioned in chapter 1 and chapter 2, chapter 3. Okay, this queue might full sometimes. Okay, so let's take a look at the right hand side. Decentralized switching using header fields. Look up output port using forwarding table in the input port memory. Okay, that means in control plane, those routers or the SDN, they will compute the forwarding table, and those forwarding table will be stored in the input port memory. Okay, and every segment, every diagram will look up the forwarding table to find appropriate output port. Okay, by using the header fields value, and usually we use destination address to find what is the appropriate output port. Okay, so we have a match plus action. So the layer 3 component will move the packet from this input port to the switching fabric and to the output port. Okay, and for this input port, the goal is to complete input port processing at line speed. As we mentioned before, the line speed could be 1 gigabit per second. So of the processing, including the blue one, the green one, and the red one, the output speed of this input port should nearly, or we say should be very close to the line speed. Otherwise, the queue might be full. Okay, so input port queuing, if diagrams arrive faster than the forwarding rate into switch fabric, then the queue size increased. Okay, that is very straightforward, right? Okay, and when we do such kind of switching, okay, as I mentioned, we usually use destination IP address, right? But take a look at the left hand side. Destination-based forwarding, the forwarding is based on destination IP address only. That is the traditional way, and that is the most of routers do forwarding based on destination address. Okay, but the new router, okay, they can forward the packet based on any set of the header fields value. Okay, for example, you can set a rule and say that if it is a TCP packet, and we deliver this packet to router A to goes to port 5, for example. And if it is a UDP diagram, and we send the diagram to port 18, you can do that. But frankly, in my opinion, generalized forwarding is useless, and we simply just don't use such kind of forwarding rules, because in the internet, most of the routers, they just want to do simple things. They just want to forward those packets based on the destination IP address. It is the most simplest way to do so. They don't have to look up different fields. They don't have to do some extra mechanism to do forwarding. Using destination IP address is good enough to deliver, and that is how current internet works. So generalized forwarding is not make sense in the internet, although you can do so, but I think it does not make sense. Okay, so we'll skip this to view graph. Okay, we will come back later. So the next part is how switching fabrics works. Transfer packet from input link to appropriate output link. Okay, so and usually in textbook we have 3 different mechanism. Okay, let's take a look at this one. We can see that. Okay, it is a traditional way to do switching via memory. Okay, that is the first generation of routers. It's the mechanism is very similar to the motherboard. Okay, so we have a system bus. So every component will communicate with each other or exchange messages between each other via system bus. So you can draw a CPU right here, because usually we have a CPU connected to the system bus as well. Okay, we have I/O port, input port, output port, we have memory. So when packet comes in at the input port, okay, the input port will send a message, send a signal to CPU and say, okay, I have a new incoming packet. Okay, so the CPU or some IC will copy the packet from the input port to memory. Okay, and we have a forwarding table right here in the memory as well. So the CPU or IC, okay, will check the packet against the forwarding table and determine where the output port this packet should go. So again, the CPU or some IC will again make a copy of this packet from the main memory to the output port, and the output port will send the packet out. So in this case, okay, the speed is limited by memory bandwidth because we have 2 bus crossing per diagram, the green one and the blue one. Okay, so but think about one thing. What is the current system bus speed? In early days, it should be several. It should be several megahertz. But currently, the system bus should be 6 gigabit per second, something like some numbers, certain numbers like this. So basically, the bottleneck is the system bus, because system bus is not fast enough to deliver, to forward the packet, because you have to divide the system bus by 2. Okay, so the bottleneck is at the system bus. So after the first generation of router, we then switch via a bus Because memory is very expensive in early days, so we have only one memory in the router. But when we have enough money, right, or the RAM cost is lower, we put RAM in every input port and output port. So we don't have to make a copy twice for to deliver a diagram. Okay, so when packet comes in, it stores at the input port memory, and after the calculation, okay, after the router decide which port it should go to, and it just simply makes one copy of the packet from input port to output port. For example, the blue one, the blue line. Okay, of course the switching speed is also limited by bus bandwidth, but you don't have to divide it by 2. Okay, currently, for example, Cisco 5600, okay, the system bus is 32 gigabit per second, so it is sufficient speed for access routers. Okay, because for example, we have 1 gigabit per second line speed, and if we have 32 gigabit per second bus, we can have a router which has 32 input and output ports, right? But there's still one limitation, one shortcoming, is that when the blue packet use the bus to forward packet from its input port to its output port, the purple one cannot access the bus because the bus can only serve one I/O device. Okay, so we don't have, we cannot send the purple one and the blue one simultaneously. So the next generation looks like this, crossbar. Let's take at this figure. Okay, so the idea of crossbar is that when you do the purple transmission forwarding, you can also parallelly send the green one, and of course, if possible, you can send the blue one as well. Okay, so in this case, we can parallelly send a forward packet, so which is more efficient. But I have to make a notice that all those mechanism, all those crossbar and the bus design, they are more likely double E students work. Okay, as MI students, usually we just know there are several different ways to do so, but we don't know how exactly those IC, how those crossbar are designed. But it is good enough for us to understand a router. It is good enough. Okay, so we simply just skip these details because we don't actually know how it works, but we know currently port are designed. Okay, the next question is more MIs. Okay, we are talking about queuing. Okay, if switch fabric slower than input ports combined, queuing may occur at input queue, right? And queuing delay and loss due to the input buffer overflow. So think about one thing. We have several different packets need to be forwarded, right? So the A, the red one, goes to the red output, and for the third input port, we have diagram B and diagram C, but diagram B also goes to the red output port. So at this time, when A occupied the switching fabric, no matter if they use crossbar or they use a bus, when A occupy the switching fabric to the red output port. B has to wait because it also goes to the red output port. But there's a Q at the third input port, right? C. Because C is blocked by B. So even if the output port, the green output port, is available right now, but because of B, C cannot be forwarded before B. That is a very this question is called head of the line blocking. Q diagram at front of Q prevents other in Q from moving forward. So in this case, C is blocked, and B is blocked as well. So that is not a good. That is not a good situation. Okay, so if it, so we think about one thing. If it is possible that if we know A is blocking B and C, but currently C, the green output port is available, could we simply just that C goes to the green output port first? So that will be more efficient. So there are a lot of different situations about queuing. So queuing is a very important thing in router. Okay, so let's take a look at some problem of queuing. So here we have output port, right? So it's very similar to input port. We still have diagram buffer, we still have link layer protocol, we still have line termination and line to send the diagram out. Okay, first part. Buffering required when diagrams arrive the fabric faster than link transmission rate, because sometimes a lot of packet goes to one single output port, so we need a buffer to buffer all those outgoing diagram, because sometimes the link speed RBPS is smaller. So when buffer might full, we should set up a drop policy, which diagrams to drop if no free buffers. So that is the reason why diagram can be lost due to congestion, which means lack of buffers. So we have several different scheduling principles. Chooses among queued diagrams for transmission. Okay, here we okay, let's take a look at this one. Buffering when arrival rate via switch exceeds output line speed. So queuing or delay or loss due to the output buffer overflow. We have several different we say queuing policy or queuing mechanism to choose. At the right hand side, for example, if buffer is full, we need to drop certain part. We need to drop a packet, right? There are several different choices. For example, tail drop arriving packet, because all those diagrams in the buffer, they already wait there for a certain period of time, right? So if you are a newly arriving packet, we simply just drop the arriving packet, because others are already waiting for a certain period of time. Okay, the other policy, which is, for example, random policy. If a new packet arrives, and you can simply just randomly drop one packet in the queue, which is okay, but that is not that fair, right? Priority. You can set different priority to different diagram. So if new packet arrives, you can simply drop the low priority packet. Okay, we have several different policy. We'll introduce some of them later. Okay, so take a look at this one. Okay, So we simply just draw a queue right here from the left hand side to the right hand side. So when a packet arrives, okay, it will be queued in the queue, and there should be a server. Okay, the server will consume the queue at certain speed, and after it serves the the packet, okay, and the packet will depart. Okay, that is the abstraction of the queue. So let's take a look at some different policy. The first policy is first come, first serve. It is as known as first in, first out. Actually, it is queue. It is very straightforward. Okay, so for this first come, first serve, the router will serve the the head of the queue first. Okay, and if the packet arrives and the packet is in the queue is full, it will simply drop the arriving packet. Okay, the real world example, for example, like you go to the train station to buy a ticket, right? Okay, that is a very straightforward one. So let's take a look at this one, priority queue. Okay, so that means in your router you have two queues, high priority queue and low priority queue, the red one and blue one, sorry, the green one. So when packet arrives, it will be classified into appropriate queues, depend on no matter what you classify your packet. Okay, so the server right here will consume the red queues first. If there's any red packet in the red queue, high priority queue, the server will serve the red packet first, no matter how many green packet in the green queue, and no matter the green packet arrived before the red packet. Okay, so here we have an example right here. Make sure you understand how to read this figure, right? That is the time. Okay, so right here, packet 1, red packet 1 arrives. So we have one packet in the red queue. So we simply just serve the first red packet. And when you're serving the packet, okay, at this moment, the second green packet comes and the third red packet comes. Okay, and after you finish serving this red packet, okay, and you'll take a look at your queue. Okay, you see green packet 2 and red packet 3 are in their corresponding queues, but because it is priority queue, you have to serve the red packet first and the red packet departures. And after you serve red packet 3 and you take a look at the queue, okay, you don't have any red packet in the red queue, so you serve the green packet. Okay, when you serve packet number 2, green packet, red packet 4 arrives, but at this moment you cannot preempt the green packet, although red packet has higher priority, but you cannot preempt the green packet because it is already being served. Okay, so after you finish green packet 2, you serve packet 4. Okay, if you don't have any packet, you simply just wait later, and you have a new green packet, you serve a green packet. That is very straightforward. You simply just take a look at the queue. If there is any red packet in the queue, you serve a red queue. But it is not that good enough, because if your red queue is backlogged means you always have some red packet in the queue. and you don't have any chance to serve the green packets, right? So green packets starves. Okay, starve. So that is not that good because green packet may don't have any chance to be served. Okay, but I have to mention something right here. Does all those internet routers implement priority queue? The answer is no. Because in internet, there should not be any packet will be considered as higher priority queue, because every packet is we mean fair. A router should not classify packet into different priorities because it is not fair. So I think most of the internet routers does not implement such kind of priority queue, but you can turn on such kind of configuration in your house. It's right here. Okay, your Wi-Fi access point or your router or your ADSL modem, there should be some mechanism can help you to turn on such kind of priority queue in your home network. So when you play games, when you watch videos which you think is more has higher priority, your routers, your Wi-Fi IPs, they can send those packets first to the internet. But after those packets goes to the internet, those routers will not will view every packet as the same. They don't have priority queue in mechanism in the internet, but you can do it at your home. Okay, because the green packet might starve, so we have several different improvement like round robin. Round robin is still very simple mechanism. We have, for example, we have 3 queues right here: the red, green, and purple one. So round robin means you send one red packet and one green packet and one purple packet, and so on and so forth, so on and so forth. So ideally, the amount of packet in red, green, and purple, they will be evenly delivered, right? So, but for example, if there's no green packet, for example, and the server simply just send one red, one purple, one red, one purple, something like that. This is very straightforward. Okay, and the round robin has another version which is called weighted fair queuing. For weighted fair queue, WFQ, you can simply just set different numbers on the queue. So the server will send, for example, 5 red, 2 green, and 3 purple in this with this amount of packet. Okay, so in a long term, the size, the weight would the amount of packet would be very close to the weight 5, 2, and 3. And of course, if you don't have any green packet, you simply just send 5 red and 3 purple, 5 red, 3 purple, and so on and so forth. So in this case, the green packet would not starve because at least it has 20% of time to be served by the server. Okay, so we have a minimum bandwidth guarantee. So in this case, the green packet will not starve. Okay, I think it is quite straightforward as well. So that's it. That is weighted fair queuing. Okay, again, we have to stop right here because the next video will be a little bit longer. Okay, so next we stop right here.